Welcome. Today we're diving into the SAGA design pattern, a powerful approach for maintaining data consistency in distributed systems. As modern applications increasingly rely on microservices, ensuring reliable transactions across multiple services becomes a real challenge. The SAGA pattern addresses this by coordinating a sequence of local transactions, each handled by a different service. If something goes wrong, compensating transactions are triggered to undo previous steps, helping to keep your data consistent. Let's explore how this pattern works, why it's needed, and how it fits into the world of cloud-native architectures. Before we get into the SAGA pattern, let's clarify what a transaction is. In software, a transaction is a unit of work that may include several operations, like updating records or transferring funds. Transactions must follow the ACID principles: atomicity, consistency, isolation, and durability. This means all operations succeed or none do, data remains valid, concurrent transactions don't interfere, and changes persist even after failure. While these principles are easy to enforce within a single database, things get tricky when multiple services and databases are involved. Microservices architectures bring many benefits, such as each service owning its data and being able to use the best database technology for its needs. Services can scale independently and failures are isolated. However, this independence complicates data consistency across services. Traditional ACID guarantees don't apply easily when each service manages its own database. That's where distributed transaction patterns like SAGA come into play, helping to coordinate changes across services without tight coupling. SAGA pattern breaks a distributed transaction into a series of local transactions. Each service completes its work atomically, updates its database, and then triggers the next step through an event or message. If any step fails, the SAGA pattern initiates compensating transactions to undo the changes made by previous steps. This approach ensures that even in the face of failures, your system can maintain a consistent state. Let's look at some key concepts in the SAGA pattern. Compensable transactions can be undone if something goes wrong. Pivot transactions mark the point of no return. After this, all subsequent steps must complete for consistency. Retrievable transactions follow the pivot and are designed to be idempotent, meaning repeating them won't cause issues. These concepts help ensure that even complex workflows can recover from failures and reach a consistent final state. Compensable transaction is one that can be reversed if needed. If a step in the SAGA fails, compensating transactions are triggered to undo the changes made by previous steps. This is crucial for maintaining data integrity, especially in distributed systems where rolling back changes isn't as straightforward as in a single database. Compensable transactions form the backbone of the SAGA pattern's ability to recover from failure. Pivot transactions are the point in the SAGA where, once passed, all subsequent actions must complete for the system to be consistent. After a pivot transaction, compensating transactions are no longer possible. Retrievable transactions come after the pivot and are designed to be idempotent, ensuring that even if they're repeated due to temporary failures, the system remains consistent. This structure helps SAGAs handle failures gracefully and reach a reliable final state. There are two main ways to implement the SAGA pattern. The first is choreography. In this approach, each service publishes events that trigger actions in other services with no central coordinator. Choreography works well for simple workflows with few services. It avoids a single point of failure and distributes responsibilities, but as the workflow grows, it can become hard to track and test, and risks cyclic dependencies between services. Second approach is orchestration. Here, a central orchestrator manages the entire SAGA, telling each service what to do and handling failures. Orchestration is better for complex workflows or when you need to add new services. It avoids cyclic dependencies and provides clear separation of responsibilities, but introduces a single point of failure and adds complexity to the coordination logic. Choreography offers simplicity for small systems. It doesn't require a central service, so there's no single point of failure. However, as more services are added, the workflow can become confusing and it's hard to track which service responds to which event. Integration testing also becomes challenging since all services must be running to simulate a transaction. Cyclic dependencies can also creep in, making maintenance harder. Orchestration is ideal for complex workflows. The orchestrator manages the flow, avoiding cyclic dependencies and making responsibilities clear. However, this approach introduces a single point of failure. If the orchestrator goes down, the whole workflow can be affected. It also requires more design effort to implement the coordination logic, but the benefits often outweigh the drawbacks in large systems. Implementing the SAGA pattern requires a shift in design thinking. You need to focus on coordinating transactions and maintaining data consistency across multiple microservices. Debugging SAGAs can be complex, especially as the number of services grows. Since each service commits changes to its own database, rolling back changes isn't always possible. Handling transient failures and ensuring idempotence are also crucial, as is monitoring and tracking the progress of SAGA. SAGAs operate across multiple services. Data anomalies can occur. Lost updates happen when one SAGA overwrites changes made by another. Dirty reads occur when a SAGA reads data that hasn't been fully committed. Fuzzy or non-repeatable reads happen when different steps see inconsistent data. These issues arise because there's no built-in isolation across services, making it vital to design SAGAs carefully to avoid inconsistencies. To address data anomalies, several strategies can be used. Semantic locks apply application-level locks to prevent conflicting updates. Commutative updates ensure changes can be applied in any order. Pessimistic view reorders SAGA steps to avoid dirty reads. Rereading values confirms data hasn't changed before updating. Version files keep a log of all operations, and risk-based concurrency chooses the right mechanism based on business risk. These measures help keep your data consistent. SAGA pattern is best used when you need to ensure data consistency in distributed systems without tightly coupling your services. It's ideal when you need to roll back or compensate if a step fails. However, it's not suitable for tightly coupled transactions, when compensating transactions occur early, or when there are cyclic dependencies. Understanding these trade-offs will help you decide if the SAGA pattern is right for your architecture. Several related patterns can complement the SAGA pattern. The choreography pattern lets each component decide its workflow. The compensating transaction pattern undoes work if steps fail. The retry pattern helps handle transient failures, and the circuit breaker pattern improves stability by managing faults. Health input monitoring ensures your services are running correctly. Exploring these patterns will deepen your understanding of building resilient distributed systems.